you. And welcome. Thank you for being here, and thank everyone else.
Thank you, Amy. Can you hear me okay?
I can.
Okay, great. Well, I want to just thank Amy and the Tulsa Geological Society, first of all, for inviting me to present today. It's great to be here and share this. So subsurface geological storage of carbon or CO2 is just one of several different options that people have been investigating. And the state of Oklahoma is obviously a great candidate for this, and just because of its deep sedimentary basins and existing reservoirs. But there have really been few published studies that have done detailed assessments, statewide assessments of the CO2 storage capacity for Oklahoma. And so over the past 5 years or so, we've been looking at the different Paleozoic strata across Oklahoma to do this type of a detailed assessment. Before I get too far, I want to be sure that I'm really kind of a messenger here. This is primarily the work of Anna Turnini, who's one of my PhD students at OU, and so everything that I'm presenting here is really the work that she's conducted. And I'm her PhD advisor at OU, and importantly, she will defend a week from today, next Tuesday, her doctoral dissertation. So she'll do a great job. So start with an outline. I'll go through the objectives of what we're doing through what we've done through this research and what we'll continue to do with some of the other formations. A little bit of background information for those that may not be as maybe knowledgeable about some of the terms that people use with CO2, talk about the location and all the data that we've used, and then get into some of the methods. I won't have time today to go through a lot of the details here, but we kind of went through kind of a 1D to 2D to 3D approach where we've taken conventional well logs, done different types of derived petrophysical logs from those to do subsurface correlations across the state to generate subsurface maps and 3D subsurface geological models and then using those models, use those to calculate CO2 storage capacity. And so then the next on the outline is the results, looking at the structure and stratigraphy, the thickness of these different formations. We're focusing on the lithological variability, petrophysical property trends, and then the actual CO2 storage capacity estimates for the lower Paleozoic, and then end with some conclusions. So the objectives, so as I mentioned, there's hasn't really been detailed statewide assessments of CO2 storage capacity. Some people use the term storage resource. So it's been relatively lacking. So what we hope to do through this is add to what has been done for the state of Oklahoma. There's been site-specific studies, but not so much statewide studies. And so this study utilizes data from a lot of well data, more than 80,000 wells across the state, and other information to correlate, map, and interpret, first of all, the Arbuckle and Timbered Hills groups, the Viola Limestone and Simpson group, and the Hunton group. And so those data, and just with that part, we're talking several years worth of work to compile the data, create databases for this, and do all the correlations. And so Anna's been very busy, and other students. And then those data were used to construct and analyze well-constrained 3D geological models to estimate CO2 storage capacity. So the results are detailed models of the structure, the stratigraphy, lithology, porosity variability, CO2 density, and then CO2 storage capacity for the lower Paleozoic. So in this case, we're talking about geologic carbon storage, and the idea is to try to store carbon or CO2 permanently within the subsurface. And across Oklahoma, there's different formations that are really ideal for this. And we're mainly focusing on today, talking about saline formations, saline aquifers, and oil and gas reservoirs, but other research that people are conducting are on some of these other types of formations, some of which exist within the state. In terms of some of the terminology, so there are specific criteria that people apply to some of these terms that are used. And so on the left here is from the CO2 storage resource management system with some of these specific terms. And there's a similar type system that everyone's probably familiar with for petroleum resources. I'm going to be using these terms relatively loosely in this. Amy, can you still hear me? I think I may have lost connection.
Yeah, I can now again, but yeah, you froze up there for a bit.
Can you see the slides?
Not right now.
Let me see if this comes back. Can you see them now?
Yeah.
Okay, I'm not sure what happened.
Okay, I was afraid it was me.
Okay. So I was just talking about some of the terminology. So I'm using some of these terms loosely. In terms of CO2 storage capacity, technically you'd have to do some type of economic or look at economic and regulatory types of constraints to define capacity. Technically, what I'm presenting is probably more related to a storage resource, some type of contingent storage resource. But the idea here is that we're doing some type of calculation to determine the amount of CO2 within the subsurface that could be stored. And there's different approaches to doing this. There's analytical approaches such as just using analogs, and as well as material balance approaches. And what I'm going to show, it would be a volumetric type of an approach, which is kind of more of a static type of a calculation. Once you do kind of more of a site-specific type of a study, you can get into more of dynamic flow simulation and look at CO2 injection and things like that versus time. But what we're looking at is more of a volumetric approach. And so the idea here is that we would estimate, looking at this equation, we're using a DOE methodology to try to estimate CO2 resources or CO2 storage capacity within the subsurface. And so the different terms of this will give us the pore volume, the density of CO2, and then this storage efficiency parameter. The Department of Energy has done a lot of work to estimate different values for this efficiency parameter. But in the end, by doing this calculation, we end up with a mass of CO2 that can be converted into so many tons of CO2 that could be stored. And generally, that's how it's reported. So there's a lot of detail here, but I just wanted to touch on this E-saline parameter, the storage efficiency parameter. So the work of the DOE, they've established for different lithologies and different environments of deposition, what they refer to as the site-specific or kind of more specific study area estimates of efficiency versus formation level, which are more regional types of efficiency estimates. And they range from about around 1.5% to about 15%. And what that is that's the volume of CO2 that could actually be stored within a certain pore volume. And they break it out into these different terms here that relate to, for example, the aerial net, the net area to the total area that you're considering, the net gross thickness, the effective porosity, the total porosity, and then how that CO2 could displace the fluids within the formation in terms of a aerial efficiency, a vertical efficiency, this displacement efficiency of the fluids. I'm not going to get into all this, but I just wanted, there's a lot of things packed into this efficiency term, this storage efficiency term. The other term that you hear people use is the supercritical CO2. And what that has to do with is that CO2 exists as a gas at the surface, but then as you increase the temperature and pressure when you store it in the subsurface, that density of the CO2 will increase and its volume will decrease. And there's a certain depth around 800 meters, which is about 2,600 feet, at which it changes phase from a gas into a supercritical fluid, which is something between, the characteristics are something between a liquid and a gas. It's dense like a liquid, but somewhat viscous like a gas in terms of how it flows through the rock formation. And so what's important to us is as it's injected within the subsurface, the volume of that CO2 is reduced significantly, so you can store the same amount of mass within a given pore volume. So there's the required storage volume is much less at subsurface conditions. So we're mainly going to focus on the Arbuckle and Timbered Hills groups, the Cambrian Ordovician. Arbuckle and Timbered Hills, the Simpson and Trenton groups, specifically the Viola limestone, and then the Hunton group. And so to do this, there's quite a bit of data that were used across the state. There's for the Mississippian, because it's shallower, there's more well penetration. So almost 81,000 wells were used to map the Mississippian. Wells with Arbuckle tops, there's about 5,500 wells that penetrate the top of the Arbuckle. In terms of digital data, the partial Arbuckle penetrations with LAS were about 403 logs or wells, and then full Arbuckle penetrations, there were 82. And the red area shows the outline of the study area for this. Goes to the south up until we get to these uplifts. And the reason why it's truncated here to the northeast is because of that supercritical phase that we were talking about. Here at this point, when you get up to the northeast, some of the formations, well, some of them are pinched out, or they're at a depth that would be shallower than about 2,000 feet. And so that's why it's terminated here. This would be specifically for the Viola limestone and the Simpson group. So this Ordovician interval, same type of tops for the Mississippian, and then wells that penetrate the top of the Ordovician, almost 40,000. So all those pink dots in through there. Full Ordovician penetrations, 343, and about almost 1,500 partial Ordovician penetrations. And then for the Hunton, because of the significant unconformity at the top of the Hunton, it's truncated in the north and northeastern part of the Oklahoma, and so the study area is reduced to where it pinches out here to the northeast, and then the southern boundary is the same as the others. And there's about 41,000 wells with tops, all the orange dots in through here to constrain the Hunton surface, and then digital logs for about 344 wells, and we use machine learning to try to estimate PE curves for some of the remaining wells that didn't have PE, so that we could do some mineralogical estimation for those wells. So in terms of the petrophysical analyses, we calculated V shale, total porosity from the neutron, and density porosity. The density porosity was determined from the bulk density. And then we use this deterministic multi-mineral type of estimation technique to estimate mineralogy and lithology logs for the wells that we had those data. And so this is called the Roma-Yuma analysis. Then those analyses were used to estimate lithology logs using this approach. And then those were used as a constraint along with all the mapping that was done to and with the conventional logs to correlate these different formations across the state and generate structure contour maps and isopac maps that were then used to create a three-dimensional grid across the state for these key formations that I'm talking about. So there's a lot on this. I'm just going to step through it briefly. This kind of is this workflow that we used, and we're coming back to that equation that I talked about earlier. So to begin with, all that information that I just talked about took years of mapping and compiling data. That went into creating this stratigraphic and structural framework, or that 3D grid. And then so the data was stored within geographics projects and patrol projects to do the subsurface mapping and modeling. And then using that, we created lithology models and porosity models that were constrained to the lithology. And then going back to those DOE estimates of storage efficiency, using the lithology models, these efficiency parameters are based on all these different lithologies that the DOE looked at. And so from this, those efficiency parameters were applied to the lithology model to come up with 6 different scenarios of storage efficiency from what they referred to as the site-specific to formation level efficiencies. In addition, then, given temperature gradients from bottom hole temperatures from the well data and pressure gradients, that information was used to construct temperature and pressure models that were then used to estimate CO2 density, so we could determine the density of the CO2 at reservoir depths. So then once all that was done, we basically have everything we need to estimate storage capacity. We have the bulk volume from the stratigraphic and structural framework. The porosity model combining with that gives us the pore volume. We have the density of CO2, 3D models of that, and then all these different storage efficiency parameters for these different scenarios. And so what we end up with would be storage capacity calculations for each of these different storage efficiencies. So kind of coming back up here to the structural and stratigraphic framework. So again, as you remember, we had a lot of data to constrain the Mississippian surface. And so to create the deeper structure contour maps for those, we generated isopac maps for the Mississippian to Ordovician interval, the Ordovician to Arbuckle interval, and the Arbuckle to basement interval. And then we added to this Mississippian structure these different isopac maps to generate the Ordovician structure contour maps, the Arbuckle structure contour, and the basement. And then those were used, as I mentioned before, to create this three-dimensional stratigraphic and structural framework. This is basically the 3D grid for the state. And so the aerial cell size, you can't see the cells on here, but the aerial cell sizes are 2,500 feet by 2,500 feet. And the Arbuckle has about 400 proportional layers, each about 6 feet thick, resulting in about 60 million cells for the Arbuckle. For the Ordovician, there's about 160 proportional layers, about almost 22 million cells in the Ordovician, and the Hunton has about 9 million cells. And so for the Arbuckle, to generate the lithology model, it's well constrained. It's constrained to this 3D stratigraphic and structural framework. The lithology logs are upscaled to the 3D grid, and so all the distribution of those lithology logs are used as a constraint in the mapping. The percentages of the different lithologies are also constrained. Those are based on these lithology logs. And then the spatial continuity of those different lithologies within the Arbuckle are constrained by these variogram parameters. And we use sequential indicator simulation to model the spatial distribution of all these different stratigraphic intervals. So this shows the Arbuckle lithology and porosity models, the lithology on the left, the porosity on the right. And as you'd expect for the Arbuckle, it's primarily dolomite with lesser amounts of limestone and shale. These models, just so we can see things, because we're looking at the whole state, they're flattened on the top of the Arbuckle, and they're vertically exaggerated quite a bit so you can see the spatial distribution of these lithologies. The yellow in here would be areas where it's a bit more silicious, this silica content. And over here on the porosity model, this shows the spatial distribution of total porosity. Again, it's flattened on the top of the Arbuckle, and so the various colors here correspond to the variation in porosity. So then at this point, we have basically all these terms here filled in for our equation, that we basically have enough to calculate pore volume. And so to estimate CO2 density, we need estimates of temperature, pressure versus depth. And so using temperature and pressure gradients, 3D models of temperature and pressure across the state were generated. And what this shows are average temperature maps and average pressure maps extracted for the Arbuckle interval from those 3D models. And then that information was used to estimate the density of CO2 and how it varies across the state. And then the storage efficiency parameters were based on the DOE information. So then from that, we can estimate the storage capacity for the Arbuckle. And it's converted from so many kilograms of CO2 to metric tons, and that's what's shown here. So many metric tons of CO2 in kind of 3D, and then these fence diagrams. And then it's normalized here. This is a map showing the normalized storage capacity in so many million metric tons of CO2 per square mile. And another way of looking at it is, and because we're kind of interested in the specific depths that we would be encountering the Arbuckle, is this is broken out by true vertical depth. So the depth you'd have to drill to encounter the top of the Arbuckle, and in kind of 200 or 2,000 foot thick intervals. And so, for example, looking at these formation level efficiency parameters, the CO2 storage that would be estimated, say, from 4,000 to 6,000 feet would be about 3 gigatons to about 6.7 gigatons of CO2. And that would account for about 6% of the storage that would be possible, not considering economics, totally for the Arbuckle. So that's how you kind of read this. It's broken out by these depth intervals. The other thing to consider, obviously, for the state of Oklahoma is seismicity. So especially thinking about injecting into the Arbuckle. And so to look at that and to kind of see how the seismicity, existing seismicity, where the areas where that occurs, the map up here on the top left is a map that was generated where we looked at known earthquakes that have occurred from the Oklahoma Geological Survey, faults that have been mapped, so the known faults that have been mapped, and also where there's been injection wells drilled. And so if we're closer to any of those three items, though, that it appears as kind of bright colors on this map. If you're farther away from mapped faults, known earthquakes, or injection wells, it appears more as kind of the kind of purplish colors on the map. And what this shows in these lower views is the distribution of magnitude 3 to or greater earthquakes and where they occur. Most of them, the surface here that you see here is the basement surface, and most of them occur within the basement interval. This upper surface here is the ground level. And so you can see kind of the spatial distribution of those earthquakes. All the earthquakes greater than a magnitude 3, greater than or equal to a magnitude 3 from 2011 to 2023 are shown. And then kind of see where some of these earthquakes are relative to the Arbuckle. This shows all earthquakes that would be within the Arbuckle zone during that time period. And you can see that where all the dots are, magnitude 3 or greater. And as you go shallower, some of these shallower areas, there aren't earthquakes that are plotted, as well as deeper. It's mainly within the central part of Oklahoma where a lot of the injection has occurred. And then this map on the lower right shows where all earthquakes above the Arbuckle zone. And kind of the same thing, you can see the distribution of these points, but then kind of shallower, there's not earthquakes that have been recorded, and kind of deeper within the basins as well. And so if we kind of put all this together, this shows areas where it might be more favorable for CO2 injection within the Arbuckle. So these red polygons would be, for example, these two kind of in central Oklahoma would be areas where there's higher porosity and moderate storage capacity at depths less than about 8,000 feet. However, there has been seismicity in this particular area that you'd have to be concerned about. This swath kind of on the northeast side would be shallower areas, about 3,000 to 4,000 feet TVD, with lower proximity to map faults or previous seismicity, previous earthquakes. Moving on to the Ordovician, the Viola limestone and the Simpson group. This again shows the lithology model for that interval, and this interval's primarily limestone with also quite a bit of sandstone associated with the bromide. The upper part of the Ordovician is primarily the Viola limestone, and then the sandstone and shaly interval is the lateral distribution of the bromide sandstones. And then kind of as you go up to the northeast, because of the uplift associated with that interval and where we're starting to get truncation, we see the bromide present near the surface. This kind of gray area in through here, and there's a little strip of it here within the fence diagram. That's some siltstone, some dolomitic siltstones that exist near the top of the Viola, the base of the Sylvan Shale, that have relatively good porosity. And so those are just some stringers near the base of the Sylvan Shale. But just because of the way we identified the different lithologies, they kind of stand out as shale, but they're really kind of dolomitic siltstones, porous siltstones. So this shows most of the porosity and pore volume within the Ordovician is primarily associated with the sandstones of the bromide. And there's an area here within central Oklahoma where there's a higher amount of storage capacity, porosity and storage capacity. And this shows pH or pore thickness for that same interval. And this is just for the Ordovician sandstones. And then this is the corresponding storage capacity. And looking at this normalized map of tons per CO2 per square mile, there's an area here where we have this higher storage capacity at depths less than about 10,000 feet, so about 4,000 feet to 10,000 feet, where we have the higher storage capacity and not quite as deep in terms of having to drill so far to inject into the Ordovician. And then kind of similarly looking at this map broken out by different 2,000 foot thick intervals, that as far as how far we'd have to drill down to the Ordovician true vertical depth. You can see here, kind of like what I showed on that previous map, you can see kind of this interval in through here of from about 4,000 feet to 10,000 feet true vertical depth. We see a little bit of an increase in this storage capacity for both the formation level efficiencies and site-specific efficiencies. Then it drops off a little bit. The only reason why these numbers down at the bottom are so low is because it's a much thicker interval deep within the basin that we've lumped together. And so if you kind of look at what we've already talked about so far, there's kind of an area within this. This is showing the CO2 storage capacity per square mile for the Arbuckle and the Ordovician superimposed on the structure maps, but there's not a vertical scale imposed here. It's just to illustrate a point that there's areas within the central part of Oklahoma where you might be able to, with an individual wells, be able to inject in both of these different intervals. So stacked storage capacity. And then moving on to the last one is the Hunton. And so this is the three-dimensional model. We've just uplifted the raised up so you could see it, the Hunton, where the Hunton is. So we've raised up the Wittrych Shale and the Mississippian. And this is what the subcrop looks like. And this is all, again, flattened on the top of the Mississippian just so, and it's vertically exaggerated probably about 120 times so you can see the different stratigraphic units. I'm just going to change the lower part here so it's not flattened, and this is only vertically exaggerated about 7 times. But you can see where the Hunton has been truncated to the north, and we have Sylvan Shale, the Ordovician, and the Arbuckle along this subcrop. So the Hunton doesn't occur all the way across the state. And so these are the data that were used to map that area within the Hunton. And on the right shows the Hunton isopack map, and you can see how it thins to the northeast and eventually is truncated. And then this is the structure contour map for the Hunton. And if we look at the isopack a little bit more, we can see here that this is just the isopack map, but superimposed on it are all the well data that shows some of these areas that I've highlighted with these polygons are areas where there's been quite a bit of vertical vertical wells that have produced these areas, getting kind of close to where the Hunton is truncated. And also people have gone back in and drilled a lot of horizontal wells here. So there's been both vertical and horizontal wells that have depleted these areas. So to the west of the Nemah uplift, it's a little bit deeper, and to the east, it's a little bit shallower and thinner. This is where the dewatering plays are. But because of that pressure depletion, there could be a bit more CO2 storage capacity for those particular intervals closer to where we have the truncation of the Hunton. And we can see that this is the lithology model for the Hunton. It's mainly limestone with lesser amounts of sandstone, dolomite, and shale. Some of these where the arrows are pointing, the yellow, the sandstone, is the Meisner sandstone development near the top of this Hunton interval. And then some of this purplish area over here to the northwest is where there's been porous dolomites and some cherts that have been developed within the Hunton. And you can see on these porosity maps on the right side of the screen that you can see that porosity development that occurs pretty closer to where we have that truncation of the Hunton to the north and northeast. And those black polygons are those polygons I showed before. This upper map is all the different lithologies, so everything is included. And then the map below that's just of the limestones, some areas where there's higher porosity, and then just the dolomites, where those would exist and the porosity within those. So then similarly, similar types of displays. So this shows the storage capacity, and then it's broken out by these 2,000-foot depth intervals, how far you'd have to drill down to intersect the Hunton. And one thing that, if you kind of remember what we were looking at from the previous plots, the magnitude of the values for CO2 storage within the Hunton is much less than for the Ordovician or for the Arbuckle. There's some areas in here where we have a little bit higher storage capacity associated with some of those porous dolomites. So it's lower magnitude of storage capacity, but still a candidate for CO2 storage. And so then kind of putting all this together, this is a composite CO2 storage capacity map. So the colors on here represent the storage capacity for all three of those intervals, the Arbuckle and Timbered Hills groups, the Ordovician, the Simpson, and the Viola limestone, and the Hunton all combined on one map, and so many million metric tons of CO2 per square mile. And then the contours would be the structure contours, true vertical depth. And then what I superimposed on this these are those polygons that we looked at along the way. The ones for the Arbuckle are the ones up here to the north and to the east. For the Hunton are these dashed polygons, and the one for the Ordovician is this one here to the south and to the west. And so you can see from this, so for example, this one for the Arbuckle, this is one where we're kind of shallow. It's got reasonable porosity, but it's relatively farther away from some of these known mapped faults or existing earthquakes. There's some areas here within central Oklahoma where you might have some of the stacked pay that I had mentioned for both the Arbuckle, the Ordovician, and the Hunton. But they might be some that you'd have to consider is they're probably in closer proximity to some of these mapped faults and earthquakes that have occurred. And then looking at that same information, that composite CO2 storage capacity in terms of a bar graph, this shows those different 2,000-foot thick intervals broken out. And then this is in millions of metric tons, or 5 gigatons, 10 gigatons, 15 gigatons. And so the areas that I was pointing out from about 4,000 feet to about 10,000 feet true vertical depth would be here where we have slightly higher storage capacity that could be encountered. The only reason why this again sticks out at this great depth is because we've lumped a much thicker interval into this from that's beyond the 2,000-foot thick slab that we're talking about in terms of true vertical depth. So what are some of the limitations? I throw a lot of information here at you, but there's always limitations. In terms of the limitations for this study, while it's very detailed, there's really limited core, especially for the Arbuckle, to help calibrate some of this multi-mineral estimation technique. And so we'd really like to have more information to calibrate this Roma-Human analysis. The estimations that we got for the lithologies seem reasonable for the Ordovician and the Arbuckle and the Hunton, but you always want to try to have as much data as you can. So that's one limitation. Few wells penetrate the basement across Oklahoma, and there's limited wells have logged the complete Arbuckle and Timbered Hills groups. We had several, but there's limited ones that have logged that. Saltwater disposal wells into the Arbuckle, they generally don't log the Arbuckle interval itself log shallower, but not within the actual Arbuckle. Where probably the most uncertainty is in these estimations is the CO2 storage efficiency. And we just based our estimates on DOE's storage efficiency parameters. So the storage efficiency values really should be estimated for these specific formations within Oklahoma. And you need to have the data to be able to do that. I would say that because of the way how we actually constructed these detailed models using the well data and trying to estimate the lithologies, and we're already really accounting for the net to gross and the specific areas where there would be favorable storage within these different stratigraphic units. We're probably really being pessimistic in terms of our estimates. They could probably be as much as twice as much as what we've come up with through these estimates, because we're just relying strictly on these DOE estimates. And it's also important to realize that CO2 storage efficiency depends on many different factors that are both spatial and temporal. For example, I mean, and one thing we also didn't account for in this particular study is changes in the efficiency that might occur due to mineralization or even dissolution during injection. So there haven't been any geochemical types of modeling done to try to address that. And then these statewide volumetric estimates are useful for identifying maybe more site-specific areas, but then you'd want to go in and do more detailed characterization and assessment where you do more detailed numerical modeling and this dynamic storage capacity types of calculations once you have the types of data to be able to do that. So the conclusions for the entire Arbuckle zone based on this work is a candidate for CO2 injection. The Arbuckle group is the thickest reservoir in Oklahoma and underlies nearly the entire state. The Arbuckle CO2 storage capacity ranges from about 149 to 316 gigatons using the site-specific efficiency parameters. And about 29% of the storage capacity is at depths between 2,000 and 10,000 feet, with the idea here that you don't want to really, it's probably not going to be economic to drill really deep wells to do CO2 injection. There are some favorable locations for CO2 storage that are at shallower depths where previous seismicity is limited and it's away from mapped faults. The Ordovician sandstones, especially the bromide sandstones, are laterally continuous, about 400 feet thick and normally pressured. Their storage capacity ranges from about 16 to 52 gigatons. And across much of central Oklahoma, about 35% of the storage capacity is accessible at depths less than 10,000 feet. And then the Hunton zone, it's predominantly limestone with lesser amounts of dolomite and chert and negligible shale. The Meisner sandstone is present near the top of the zone across central Oklahoma and the Anadarko Shelf. For the Hunton, the subcrop region forms a stratigraphic trap, and areas with dolomite having higher CO2 storage capacity, like in Major County, are candidates. Regions with significant hydrocarbon production that I discussed have lower reservoir pressure and might have higher CO2 storage capacity because of that. For the lower Paleozoic strata, central Oklahoma seems to exhibit higher storage capacity at depths less than about 10,000 feet. And I just want to end, I want to thank all the different sources of the data that we had that we compiled to do this, from Inverest, the Oklahoma Geological Survey, Oklahoma Corporation Commission, and the Mid-Continent Geological Library. And then thank LMRK for geographics and Schlumberger for Petrel. And then I especially want to reemphasize that what I'm kind of the messenger here. Anna Turnini is the PhD candidate that was one of my students that she'll defend next Tuesday, March 4th. So this really everything I presented is the work that she's done over the last 4+ years, and she's done a lot of work. And the last thing, since I am the director of this school here, I did want to put a plug in for the AAPG Geosciences Student Research Symposium and Expo is March 14th, Friday the 14th. So if there's any students or faculty out there This is open. It's free to all students from anywhere. They can come and present a poster for free. There's short courses in the morning and networking with different oil companies that will have booths. And then there's a poster contest that there's significant prize money that will be awarded to those students. So you can go to our webpage and get more information, or scan this QR code to get information. And I greatly thank the support of the AAPG Foundation for being able to put this on. So with that, I think, I don't know if there's, can answer questions or how you'd like to do this, Amy.
Yeah, that was great. If anyone has a question, feel free to just raise your hand or put it in the chat, and we can answer a few questions. I have a few.
Yeah, sure.
I'm just wondering about that efficiency variable from the Department of Energy. Is that based primarily just on lithology and depth and pressure, or kind of what?
Yeah, it's a bit involved. They did a lot of detailed modeling and to back out those parameters, and they did that for different environments of deposition and with different lithologies, and did a Monte Carlo type simulation to derive those different efficiency parameters for those different lithologies. However, it's never going to be the same as, you know, the Arbuckle, and it's never going to be the same as the Simpson and the Viola or the Hutton. And so, I mean, it's a good starting point, and different authors, different people studying CO2 sequestration have used those parameters. But after you probably get into some of these more site-specific studies where you can gather more information, you could then develop your own efficiency parameters for these different formations and use those that would be tailored for the Arbuckle or tailored for the Hutton. But as a starting point, we use those DOE parameters. Okay. And there's some different publications I could point people to that describe the details of how they generated those.
Okay. And we've got a question from Steve out there, it looks like.
Let's see. Go ahead.
Yeah, I'm Steve Dorches. Thank you, Matthew, for your presentation. I was unfortunate that I came in late. I know that your focus was on the CO2 storage capacity. How much work is being done for natural gas storage, you know, with this continued overproduction of natural gas, and unfortunately a lot of it being flared or vented?
Oh yeah, you know, I'm not actually familiar with a lot of people doing specific work for natural gas storage, at least in Oklahoma. I know other states they do this routinely, but I'm not as familiar with that.
Yeah, the main application nowadays has been to support power generation swing periods, and
Yes.
also to feed pipelines. I know there's pipelines crossing Oklahoma. I was involved for years in North Texas and Louisiana's natural gas storages. And the ideal application is relatively shallow formations that have containment, right?
Yeah.
And ideally, gas cap type structure, or at least gas overlying liquids.
Yeah.
With substantial storage space, with as much capacity as there is in Oklahoma, and pipelines that do cross it, there might be opportunity there. And I know there's going to be a big.
Yeah.
Go ahead.
Well, I was just going to say there's going to be a big push. You see what's going on in Texas, all these data centers cropping up where there's natural gas supplies. And what happens though is that there isn't enough stored gas storage capacity to backstop that in peak periods. And it's been really hard to get greenfield storage projects off the ground, really of any kind of gas, particularly CO2. We tried to do a CO2 EOR project over in Louisiana back in 2012, and there just wasn't enough reserves to justify that on liquids recovery. it would have been a good storage reservoir to just cram CO2 into, but that wasn't making any money for anybody. So these kind of hard to make any money off of this CO2 underground.
Right. Yeah, I would assume moving forward that there's probably going to be a lot more interest in enhanced oil and enhanced gas recovery using CO2, and as you mentioned, the CO2 storage moving forward. But I haven't personally looked at that, but I'm sure there will be a lot of interest in that. There was a question by James Howard.
Thanks, Matthew.
Yeah, you bet. James asked, how much is known about supercritical CO2 behavior in saline waters? Does it remain in supercritical state and therefore able to displace water, or does it dissolve into the brine? I think both. I think that the idea is that it would be it's compressed. The idea is it's compressed at the surface and then injected into the subsurface where it passes that temperature threshold, and it would stay in a supercritical state within the subsurface formation. But I mean, some of it could, this is where the geochemistry comes in. So some of it could maybe initially cause some dissolution of the formation. It eventually could go into solution within the saline brines, but then eventually, with enough time, actually precipitate and form carbonate minerals within the formation. But that's an excellent question. That's actually an area that people are looking at where there hasn't been as much research. People are trying to understand the rate of these different chemical reactions in these different sedimentary rocks. They're also looking at things like basalts and the rate of these different reactions. And so that's an excellent question. And so I don't have a specific answer, but that's something people are very interested in.
Do you have any more questions from the audience?
If you know of any students who want to present a poster or just come and attend, please let them know about the expo. You don't have to present a poster, you can just come and attend.
I would like to make a comment about that question that was just raised. You know,
Yes.
CO2, supercritical CO2 has been proved with recent test facilities to be an excellent media for power generation with a much smaller turbine assembly required compared to gas turbine fired power. So, you know, there is ways to make money out of CO2 producing energy, and not just through EOR. If you want to look on my LinkedIn site, I've got a picture of a skid the Canadians built, and there's been a lot of Southwest Research Institute work on supercritical CO2 being used to generate electricity. A lot of opportunity there.
Good.
Really interesting.
Thank you.
Yeah. Thank you, Steve.
Do you have any others? I have one more kind of along the lines of the previous questions too. Has there been much research into how far the supercritical CO2 will extend away from the wellbores, or kind of what the lateral continuity?
Yeah, good. Not that I've seen. I'm sure people are looking at that, but what they've done is we've done estimates of, you know, just initial estimates like plume behavior with certain volumes of CO2 injection, but those are just using input parameters that are estimated versus, you know, there's not a lot of sites where there's more specific site-specific parameters that you can use to insert into some of these flow simulations where you're trying to look at plume behavior versus time, say over 10, 20, or 30 years. But people are looking at that, and then they're also looking at kind of the rates of some of these geochemical reactions through time.
Okay. Great. Well, if we don't have any more questions, we'll let everyone get back to their day. Thank you so much.
Thank you
for presenting to us. We will spread the word about the Student Expo also.
Okay.
And hope to see you again soon.
Yeah, thank you for the invite. Bye.
Thank you. Bye.